proton therapy. And it was a fantastic, I should say, presentation, and it was brilliant. And I was really excited to see that he was talking about those concepts. Okay, I mean, as a kind of a guidance, if when you're gonna talk about the radioactive decay, and as you know that you have to connect it with the cancer, you have to think that you can think of the radiation therapy and the proton therapy, which is a far interesting topic then. And by the way, be very quick with your assignments and your homework and your presentation, because we have almost in 2 weeks we have to finish the class. Then it means that you have to be quick because you do not have much time. Okay, and still nobody has, it seems that nobody has submitted any work. Yeah, where is Philip today?
I don't know, but can you move the paper like right a little bit, or
is it
camera?
Good?
Yes, that's good.
Awesome, awesome. Thanks for letting me know. Thanks, Faris. It's always helpful when you say that, for example, you do not have a good view. Otherwise, I'm writing it for myself, which it doesn't make sense. Okay, then now, let's start. Guys, please listen to this session very carefully, because all the things that we covered today is going to be the exact technique which you need for your, I should say, your assignment, which is due by next Sunday midnight then please extra attention. Okay, the thing that we are just going to do right now is this. We are planning to do some examples. Okay, do some examples of, let me give you this. I think on the question number 69, on your assignment questions number 69 to all the way to 76, you need these kind of concepts in order to solve it. I'm just going to solve question number 75, which is part of your assignment. Then essentially, if you see it right now, not only are one question ahead, but at the same time, you know the techniques to deal with the rest of it, because these questions are very interesting to have this on the exam. Okay, the question is this. You have the cosine of, let me put this paper aside from the other side. Okay, we have this, we say that, okay, the function that we have is this. We say that the cosine of, I give you a function. Let me take it here. Hope it should be fine. We have the function f of x, which is equal to the cosine of And guys, don't be so sad. Today is the last day that we are dealing with the trigonometric function. In case if you are so fascinated by the beauty of these type of functions, don't be sad. You may have it again next term with the advanced function. Square root of 12 plus x squared. Okay, now guys, look at that. Look at this function. It's a beautiful function. Look at that. This is, okay, so I got the message. Okay, this is a beautiful function, but look at that. Everyone can see what I have written?
Yes.
Yeah, f of x is a forward function apparently, which it has only single variable x, which is the cosine of sine inverse of argument, which is x over square root of 12 plus x squared. I told you that we can look at these functions as a mixture model. Why do I call that mixture model? Because if you look at that, you see two things. You see that for your single variable, which is x, at the same time, the inverse of the sign is transforming it backward. It's transforming it from the range to domain because that's an inverse function. But at the same time, the whole argument is being transferred forward by this forward transformation of the cosine of the whole argument. Then you see something is pulling, something is pushing at the same time, and who knows who is going to win. And that's why we call these type of interesting function a kind of a mixture models, a type of the functions that at the same time you have inverse transformation or backward transformation, and at the same time simultaneously you have forward transformation. That's this function. Look at this function. This function seems not as easy as it sounds. If you just want to find the domain, it may be not as easy as it should be. We want to plot it. It seems very complicated. Then now the thing that we want to do is that we are going to simplify the evaluation of this function, of this mixture model, as I'm going to call this. But how to do that? Guys, look at the technique because that's what you need that for your assignment. We said that previously. We call whatever is inside as the inner function. I call that inner or core. We called a kind of a rule. I call that the onion rule, like the onion, which has different layers. And we call the cosine, which is a forward transformation, and it goes up outside. We call that the outer, which like the layer of the onions, they wrap the core of the onion, which is the core of the onion, the inner function. Guys, hold on a second. Somebody called me. Okay.
No problem.
Okay, now, what do we have there? We have this one. And now what to do? Imagine that, for example, Farius is going to cook. Farius, do you like cooking? Farius?
Yes, I like cooking.
Yeah, that's nice. Imagine you want to start the cooking, you have an onion, and you cut the onion in half. Imagine that onion is this. You cut it in half. With the knife, you remove, I should say, the core of the onion. The core of the onion is the one which comes as an inner function. You peel this out, you put this on the table, on the plate, which is this function, which is the sine inverse of x over 12 plus x squared. And while you just put that Farius on the plate, on the table, for example, Gloria comes with Shen and they ask you what is that on the table. You can call it anything. You can call it dumpling, onion, you can write it. But I like always to call this alpha because it's alpha man. It's always easy to write the alpha. That's what I did. Then the thing which I did was first, I removed the core of the onion from it and put it on the table, named it alpha. But I remember also that I learned something from Thursday last week, that it was something like that, that I said that when I look at this function, when I see the sine inverse, look at this, the function which I have here is the sine inverse. Is the sine inverse. And the sine inverse, I told you, it's with the inverse trigonometric function, it's not always easy to work with them. And we are always looking for some strategies to just have forward transformation rather than having backward transformation. What was a trick which we learned? The trick was this. I'm going to write it here. The trick that we learned was this. We learned, Gloria, that the sine inverse of the x equals to the x, which essentially was the thing that we learned, that the composition of an inverse trigonometric function with its own function, it always gives you the argument itself. For example, you have the sine inverse of an apple. It gives you the apple. You have sine inverse of a dumpling. It gives you the dumpling. You have sine inverse of the x. It gives you the x. You see, there is no headache. It takes you out. Then I'm going to use this thing which I know in order to take sine from both sides of this equation to have less headache. What do I mean? Okay, what do I mean? The thing which I mean is this, that we say that, okay, we have, now I take the sine from both sides of this equation. Then what's going to happen? It's going to be sine. Everybody sees this color which I'm writing there?
Yes.
Nice. Then we get the sine of sine inverse of x of 12 plus x squared should equal to what? To the sine of alpha. Correct, everyone?
Yes.
Now look at this one. I rebuilt the same identity. The sine of inverse of the sine, this is there. You see that? You see these two functions from the same nature, the composition? Then it means that the whole argument can go outside, because I told you if you have sine of inverse of the sine of a dumpling, it becomes what? It becomes dumpling. The sine of sine inverse of a melon, it becomes a melon. And sine of sine inverse of square x over square root of x plus 12 becomes what? The same thing. Then what do I get at the end? It becomes this. It becomes x over, just hold on a second, guys, please. It's moved from the school. Hello, Mo. Hi. Then what do I get is this. It's going to be the x, and it's going to be 12 plus x squared, which equals to what? Sine alpha, correct? That's the final thing which I get, because sine of inverse of the sine of the whole argument becomes its own argument, and also on the right side I have the sine alpha. You see that, guys?
Yes.
Good. Any questions?
No.
Thanks, Rose. How about Philip and Gloria and Faris?
No.
No from Gloria. How about Faris?
Like, actually, I didn't understand it.
Oh, you know why? Because probably didn't check the lectures from a couple of days ago. But I think, Faris, the suggestion which I have for you is this. Stay up with this class, take notes as much as you can, and try to understand as much as you can. When you go back from the lectures from the Friday, we covered this lesson on Friday. When you review the lesson for Friday, you understand what's happening now. But I recommend you to watch these lectures, okay? Because when you see the lectures on Friday, you understand this, okay?
Okay.
Awesome. But please make sure that they watch the lectures from Thursday and Friday and also yesterday. Thursday, Friday, and Monday. Okay. And now, awesome. Thanks, Ferris. Now I'm at this stage. That's the thing which I need. And the onion, which Ferris cut in half and removed its core, and now it looks like this. And now Ferris wants to put that inside the oven and make a food for us. Let's see how it works. Ferris, you're gonna do some cooking today for us, it seems. Okay, now I have this one. I have x on top. I think it was 12 plus x squared, huh? 12 plus x squared, what's equal to sine of what? Sine of alpha. And now, guys, look at this. When you do your assignment or whenever you are doing this kind of stuff, it's going to be your assignment, any project, anything that you do, always look at this one. We have a trigonometric ratio, which is the sine of an angle, which is going to be called alpha. Always remember, when you have these basic trigonometric ratio, which is sine, cosine, secant, cosecant, tangent, cotangent, these basic ones, always and always, there is a basic geometric representation for them, which it gives you the whole information you may need for the entirety of the problem. Huh? And how it works, I'm going to explain that to you now. The geometric representation, it becomes two parts. I'm going to cover both these parts today. One of them, the one branch of the geometric representation, because of the sine alpha, you can use the right triangle, or the second part, which we did cover that also yesterday, it was the circle, which we build the right triangle on a circle. And now, I do not need, the choice depends on me, but it's way easier now to just use the right triangle. I use a right triangle when I do not have numerical values. For example, the function is with the x. Then I always know that it's much easier to use a right triangle formula. How is that going to work? I'm going to draw a right triangle formula. I'm just going to draw a right triangle. I see that, okay, I'm just going to call one of the angles alpha because I'm looking for the alpha. And the plan, what is now then? That's the lesson that we covered maybe a month ago. And we said that we are going to talk about plotting a right triangle and solving a right triangle. What did I mean by solving a right triangle? In a right triangle, we have three sides and three angles. Which one of them is, we know that it's going to be 90 degrees because that's why we call that right triangle. The purpose of solving a right triangle was what? The purpose was to get information about all sides, how much is their length, and all the angles. If I know one of the angle is alpha, I know the other angle is going to be 90 minus alpha because one of the angles I know it's 90 for sure. But now, I know then everything at this first step. I know everything about the angle. I know alpha. I know 90 minus alpha. I know that this is 90. And the other thing which I need, and this is very important, is that to get the information about the sides of the right triangle. How much is their length? And how can I find it? Based on the single trigonometric ratio. It becomes a golden ratio here for you. You have to love it. And now, look at sine alpha, which is this ratio. The definition that we talked about that on the right triangle of a sine of alpha was this. Sine was decided based on two lengths. The length and the side which alpha is looking at, if you imagine this is your eye, and you're looking from the alpha, you see this side, correct? Then this side has to be divided by the hypotenuse of a right triangle in order to define the sine of alpha. That's what we did, correct? Everyone remembers that?
Yes.
That's right. Then I have it defined here. I have this ratio. The numerator, which is the place for the side which is in front of the alpha, is x. Then I know this is going to be the x. And the denominator, which I know that's the place for the hypotenuse of this right triangle, is given as square root of 12 plus x squared. Then I know that this side is very easy. Then it becomes 12 plus x squared. Do you see this green light, green color, guys?
Yes.
Awesome. I'm so glad. Okay, now, what's the problem now? The problem is my right triangle is solved or not yet? Is it solved? I have all the angles and two lengths, and I do not have this length. And it means that I haven't yet fully solved this right triangle. And now, look at this. And now, what I can do is this. I say, okay, the thing which I'm going to do is I come and find this side. What is that side going to be? I use what? I use Pythagorean Theorem, which it means that it's going to be the root of what? The root of this one squared minus this one squared. It means that 12 plus x squared minus this one x squared, which it becomes how much? 2 times square root of 3, which is essentially 12, the square root of 3, because it becomes 12, then you can square root of 12 becomes what? Becomes 2 times the square root of 3. And now, what's going to happen now? It seems that right now, the right triangle is solved, correct? I have every information about the sides, and I have every information about the angles. Everyone is fine so far?
Yes.
Yes? And now, what was the problem? I was supposed to find the cosine of this inverse transformation. This inverse transformation, it was the core of the onion, which Ferris removed it from the heart of the onion, put that on the table, and called it alpha. But it means that I have to find f of x as cosine of the alpha. Now, I know that I have to find what? I have to find cosine of the alpha. Now, the cosine of the alpha, it's going to be here. What is cosine of the alpha, guys? Based on the definition that we know, and we covered that of the cosine of the alpha on a right triangle, we said that the cosine of any angles on a right triangle, if the alpha is this angle, it becomes a ratio that its numerator becomes the length of the adjacent length, because we have 3 lengths. One, the opposite, which is used for the sine, the adjacent, which is used for the cosine. The adjacent is what? How much is the adjacent length?
2 square root of 3.
That's right. Divided by what? The hypotenuse. How much is the hypotenuse?
Square root of 12 plus x squared.
That's so true. And we got this expression. And now, guys, any questions so far?
No.
Nothing? How about Gloria and Faris? I know Faris has to do some kind of review, but so any questions yet?
No.
No from Gloria. How about from Faris?
No.
Awesome. But Faris, try to learn as much as you can. I am sure when you do, I should say, when you do the reviews from Thursday and Friday lectures and also Monday, which is all of them are recorded on the website, you know they are easy stuff. But guys, the final point and the most beautiful thing which I want to say is this. I'm going to go back to my function. Look this function. It's a mixture model of the cosine and inverse of the sine. You see that? Which is very hard to work with them. But with this technique, I call that the onion technique. I named that technique myself. If you Google it, you do not find anything for it. With the onion technique that you learn, you were able to transform this configuration into this. It's now 2 of the square root of 3 divided by 12 plus x squared of x. You see that? They are the same thing. And you see this function, it's way easier than the mixture model of the cosine with inverse of the sine. Isn't that easier, guys?
Yes.
Yes? And you see the beauty of the trigonometric function. You had one horrible looking function. You are not comfortable working with this function. You say, no worries, I'm gonna break you. I'm gonna bring you a knife and cut you as an onion. Cut you as an onion, and then you look like this, and you still have the same taste. Isn't that beautiful, guys?
Yes.
Yeah, and now you see that if you do not like an onion, have a knife, cut it in half, and cook it to become like this. And essentially, they taste exactly the same thing. The taste of this function is as the taste of this function, but this one is easier to swallow it. Okay, any questions, guys, before we go to the next example?
No.
No? Okay, nice. Okay, now we go to the next example, which I want you guys to give it a little bit try to do that. What we are gonna do is this. Okay, let me, it was question number, this one, it was question number 75 of your homework. Now I'm just gonna do question number 74 of your homework. Question number 74. For question number 74, question number 74 is talk about the tangent. I'm going to give you a function f of x equals to the tangent of this very interesting looking function arc secant of five divided by 2x. Okay, this function. Everybody sees what I have written? I have a mixture model, which is f of x equals to tangent of arc secant of 5 divided by 2x. Give it 1 or 2 minutes to to analyze it, then I'm just going to solve that for you. Also, in the meantime, while you are working on your own stuff, I'm gonna slowly work on it. And as I learned from Ferris, I'm gonna have a very sharp knife, and take the knife, cut this onion in half. And put it on a plate. On a plate, and I call that one arc secant of, let me choose arc secant of 5 divided by 2x. I'm going to call this, guys, are you doing it yourself or are you listening to me? Or I'm just talking to myself? You can work on your own at the same time I'm working it here. Then you can check if you get to the same answer. I'm going to call this alpha. That's the core of the onion, which I borrowed the knife from the Ferris and put it here, cut it in half, and that becomes the core of the onion. And I call it, in case if Rose asks me, what is the name of the thing which you have a plate on it, and that's on the table, I call that, this is alpha. Okay. Okay, guys, from here, I think it's good that you listen to me because you may not have seen this identity before. Look at this, the same trick. We have two functions. One function is what? One function is secant and the other one is arc secant. I'm gonna follow the same principle which I learned, and I'm gonna say, okay, I'm gonna make a composition of the secant of arc secant of the x. Again, it's going to be the x itself. There is no exception, because there should be no exception, because if you remember before the COVID-19, when we were in the physical classroom, we saw that as a general principle that the function composition which is inverse always gives the argument which is inside. It can be sine, cosine, secant, cosecant, tangent, cotangent. Then we have the secant of arc secant of the x. You know that the secant inverse and arc secant, they are the same thing, but two different ways of writing. It depends on which one you prefer to write. Becomes the x. And now, what I'm going to do, I'm going to follow this principle here. I'm going to take the secant from both sides of my identity, from my expression, which it becomes arc secant of 5 over 2x becomes now what? Becomes again the secant of alpha. Any questions, guys, so far? Everything is clear for everyone?
Yes.
Yes? And now, the next thing which I'm gonna do is this. I'm gonna come over here and say, now look at this. Look at these two functions, secant, composition with the arc secant, which it reminds me of this identity, which it shows that whatever argument do I have, even it can be an apple, it can be a melon, it can be a dumpling, it can be a sandwich, I remove it out. Then what do I get at the end if I do this? Then it comes as 5 divided by 2x should equal to the right side, which is the secant of the alpha. Correct, guys? And that's the thing that our onion, after cooking it, before cooking it, it should taste like this. Any questions, guys, so far?
No.
No? Okay, now, I'm just going to move to the next page and solve it from there. I'm just going to rewrite it that the secant of the alpha becomes 5 divided by 2x. Then what was it? It was secant of the alpha was, what was the expression? 5 divided by 2x? Okay, now, I'm just going to start from here. And I'm just going to start from here, but you know that from right now, we have to do what? We have to do some kind of a geometric representation for this for this ratio that we have. And now, what can I do? The thing which I can do is this. I come here to say what? I come here to just have a geometric interpretation as the things that we have done so far. I'm just going to I have two methods of the geometric representation, circle and the right triangle. I'm just going to use the right triangle as long as I do not have a numerical value. For example, 2 divided by 3 or -1 divided by 2. When you have x as a secant of the alpha, it's much easier always to use the right triangle. But if I had, for example, the secant of the alpha becomes, let's say, 2 divided by 3, then I use the circles as a geometric representation. It's a right triangle. One of them is 90. I have now 2 sides. The thing which I'm going to do, I'm just going to come here to call this, let's say, the angle which I'm talking about, it's alpha. And the next thing which I'm going to do is that to solve this right triangle based on the information which I can obtain and infer from the sine of one single angle. Because based on the previous example that we saw, we can understand whatever we want from this right triangle, from this simple trigonometric ratio. Then what it can be, it becomes like this. I look at this one. I know that about the angle right now, I'm totally satisfied because I know that's alpha, that's 90, then logically this one is going to be 90 minus alpha. But about the sides, I know the definition of the secant of the alpha. What is the definition of the secant of the alpha, guys? It's what? Sorry, what?
R divided by x. 1 over cosine x.
That's so true. 1 over cosine of the x, which, as you know, the cosine of the x, it's going to be what on the right triangle? Becomes, the cosine is what? The cosine is the adjacent length. That's right. It becomes the adjacent length divided by what? Divided by the hypotenuse. Remember that from the previous example? But because it's the inverse of the cosine, you have these things reversed. It means that the secant can become what? The secant now, alpha, becomes now the ratio of the hypothesis divided by the adjacent, because it's the inverse of the cosecant. Then now, when I look at this ratio, then the numerator should give me the hypothesis, which means that this one, it's gonna be the 5x, no, sorry, it's gonna be the 5, not 5x, and the adjacent, let me erase this, the adjacent is gonna be 2x. Then it's going to be very easy to find the other sides by the Pythagorean theorem, which is going to be what? Which is going to be 25, the hypothesis squared minus 4x squared, which is the square root of this one. Any questions, guys?
No.
No.
No, everyone is fine. Then you see that based on the thing that we know that the secant of the alpha is the inverse of the cosine, then I know that the secant should be the hypothesis length divided by the adjacent. Then numerator corresponds to the hypothesis of the right triangle, which is 5, and the denominator 2x should correspond to the adjacent length of the alpha, if the alpha is this. And the other side is going to be the Pythagorean theorem. You say that the square of hypothesis minus square of the adjacent, taking the square root, it gives you this length. Now we fully solved this right triangle. But not go so far. What I was looking for the tangent of this expression, which Ferris called it alpha, as the core of the onion on the plate. And now I'm looking for the tangent of the alpha then. Then I should be done. As long as I have solved the right triangle, I can get all possible information about its geometry and trigonometry then. Then it's a safe site to solve this like that. Then it means that the tangent of the alpha, and we finish this before we go for the break, the tangent of the alpha becomes what? We have two definitions for it. We have either the ratio of the sine divided by cosine. When you follow that definition, you get to a final definition that the tangent of the alpha, that's what we covered that many weeks ago, that the tangent of alpha becomes the opposite side. The opposite side is what? Is 25 minus 4x squared divided by the adjacent, which is going to be what? 2x. And now we are done. Because we know that the definition of the tangent of the alpha on a right triangle is this: the opposite side of an angle divided by the adjacent. If the angle is alpha, the opposite is this, the adjacent is this, and we solve these values. Then we get to this point. Then you see that instead of expressing f of x as a tangent of arcsecant of 5 divided by 2x, you can express it instead as square root of 25 minus 4x squared divided by 2x, and you will see that with this expression, there is no trigonometric ratio. In case if trigonometric ratio is too sweet for you, then you can sometimes convert from this expression to this expression, and they should the same taste. And they are essentially the same expression, the same function. Any questions, guys?
No.
Everyone is fine?
Yes.
How about Gloria and Ferris?
Yes.
And Gloria? Gloria? Okay. And Ferris, also, I know that this is stuff because you didn't check, you weren't for the inverse function, the inverse of trigonometry. All of them is that, but they are very easy. If you check those videos, these things are like the easy as piece of cake. It's the easiest part of the math which we have covered. But please make sure that you check the videos mostly from Thursday and Friday last week. Okay?
Okay.
Awesome. Then if you have no questions, let's take a break. Now time is 12:12. Come back by 12:30 now. Come back by 12:28 then. Okay?
Okay.
Awesome. See you later, guys. Then we solve more problems then. See you later. Great. Now we are just coming back from the break, we're gonna do some more examples. Then I should say we can finish it today, and we start tomorrow by something very exciting, which we're gonna talk about the series and sequences, which it's everywhere in the math. You're gonna see lots of those things around, and so much with relevance to the things that we're gonna do. Okay. Now, the thing that you're going to do right now is that I solved those examples for you, but I just solved 74 and 75. And now you're just going to do other examples that I'm going to do 71 now. Essentially, you are left with fewer choices to solve. Then the rest of the activity is going to be very easy there for you. Okay, now we're going to deal with the type of, I should say, the exercises that you may need the second type of the geometric presentation. Still, we're going to follow closely the onion rules that we develop for this kind of mixture problems, but the geometric representation is going to be a little different. Okay, now I'm just going to solve this one. I'm just going to say I give you an expression. It's not going to be a function because we do not have a single variable in the main arguments of our mixture model, but instead we have this expression that we have the sine of inverse of the tangent, which we can call it also arctangent. It doesn't matter, it depends which one you prefer to write. Square root of 5 divided by 2, and I'm just going to close it. You see, for this one, I'm not coming here to say, okay, I didn't call that f of x. Guys, you see what I have written?
Yes.
Clearly? Yes, Rose?
Yes.
Yes, Ferris and Gloria?
Yeah.
Awesome. Look at this one. For this one, I didn't mention that it's going to be f of x. It's because I do not have any x. This is not a function. It's an expression which you have to evaluate that. Then we do not have a function to start with. And that's the difference when we go to the geometric representation. That is going to be a different version. It's going to be more trick involved. Then please listen to this very carefully. And also for you, Ferris, we did something similar yesterday. If you please check the video from yesterday, towards half an hour at the end of the class, we did something very similar compared to this. But it was more difficult, the one which we did yesterday.
Okay.
Thanks. And now the thing which we want to do is that, again, imagine Ferris is coming here. Still, he has a very sharp knife. He's going to remove the core part of this onion. I'm gonna take this outside, put that on a plate, and we're gonna call this one what? We're gonna call this tangent inverse, which is the core of the onion of square root of 5 divided by 2. We call that, in case if Rose or Gloria asks first, what is that? We're going to call that alpha. You can call it anything you want. It doesn't matter. When we are there, we learned it from yesterday. Exactly, Faris, it was a lesson from yesterday. If you want to check the videos from recorded videos, you can find it at the beginning of the session from yesterday. That we said yesterday that the tangent of inverse tangent of x, any argument, again, is going to be the x. You see, these things are always the same because they are coming all from the fundamental laws that we learned months ago about the composition of an inverse of a function with its own that always gives you the argument. Then based on the things which we know from yesterday, now you may guess what's going to happen later. And the thing is that going to be like this. I'm going to come here and I just put what? Take the tangent from both sides. I'm going to get tangent of the tangent inverse of square root of 5 divided by 2, which I know should equal to the tangent of the alpha, because I know that I took the tangent from both sides of the equality. Then I have to impact it on both sides, to the left and also to the right, because I have to preserve the equality, and that's the reason I take the tangent from both sides. And guys, you should not be surprised you see that the function of the same nature. You have the tangent and you have inverse of the tangent, which it means that the composition of a function with its own inverse, which we know that it's going to be the argument itself. Then here as an argument, you can have melon, you can have dumplings, you can have ice cream. It gives you the ice cream itself. Then what I'm going to get here is this. I get the argument itself, which is going to be the square root of 5 divided by 2 should be equal to what? The tangent of alpha. And now, this is the thing. This is the plate. This is a dumpling which Faris has baked, has made, prepared, but now he needs to put that inside the oven or use the steam to cook it. Faris, do you love dumplings? Now, here are there. Then we talk about the tangent of the alpha, which is the square root of 5 divided by 2. Any questions so far?
No, I'm a little bit far away from my phone. I go to bathroom, and when I come back, I hear it, but I couldn't open my microphone.
No worries, no worries. It's totally fine. No problem. And now, what I'm going to have here is that I'm just going to take it to the next page, and I do the geometric representation for this one. I'm going to do the geometric representation of what? Of this one, that the tangent of alpha, it's equal to square root of 5 divided by what? 2. Now I'm just going to work on this. Everyone sees what I have written?
Yes.
Yeah, awesome. Now, okay, now you see that now we have, as usual, the thing that we are interested is that we see one single geometric ratio, so one single trigonometric ratio, which is a tangent of the alpha. which it reminds you of the fact that you have one optional tools, which is the geometric representation of the tangent of the alpha and the alpha itself. You have either, and guys, listen to this part very carefully, and that's where it's going to be different from our previous examples, which we covered that before we go for the break. Previously, for the geometric representation of your ratios, when you had x involved because it was a function, with the function, it was easy to solve a right triangle as a geometric representation of your ratio. But for this one, you do not have a variable x or z or y or anything. You have only a numerical value, which is the square root of 5 divided by 2. Then, as a result, what's going to happen? The thing is that in order to do that, I'm just going to do the second part of the geometric evaluation, which the second part is going to be what? Is going to be using the circles of the geometric ratio. I'm just going to have my x and y axis. That's the only way they are becoming different. And x. We may also add something to this, which we didn't talk about that before. Then please listen with so much tension. Guys, do you see this circle or no? This is too blank. I have a circle around. You see that or no? Maybe not.
It's hardly to see.
Yeah, that's because of this is a pencil and this is not. But look at that. The sections which this is intersecting with the x, I'm plotting it with the black. You see these points? These black ones, they show the intersection of the circle with my axis. You see the black points, huh?
Yes.
Yeah, it means that it shows roughly the size of my circle. And guys, also the thing that you have not seen that before, I don't know if I covered that in the